everybody. Today we're going to talk about a very interesting topic here called graphing rational functions. And we've graphed a lot of things this year, things like lines, linear equations. We've done a little bit of graphing with parabolas. We're going to talk about that more in a couple weeks. We just got done spending some time talking about graphing exponentials. So curves and so forth, different functions graph and they look different in different ways. Well, rational functions, many times, they look something that might look like this. Now, it's not always true, but they look like curves that tend to approach a line. See how this line out here is approaching the x-axis, and this line is approaching the y-axis. They tend to approach a line, and we call that line that it approaches, we call it an asymptote. This particular one right here is the vertical asymptote. Vertical asymptote. I'm going to write the whole thing out. And this one here we would call the horizontal asymptote. And these graphs typically approach these asymptotes. They don't actually cross those lines most of the time. And we can use these asymptotes as a way of helping us to graph these. You also notice that the graphs you're going to get many times have more than one branch. This one has two branches. It's got a branch over on the down here in quadrant 3, and it's got a branch in quadrant 1, but sometimes their branches are in different places you might not even expect them to be. So we're going to practice graphing a few of these, but the thing we have to start with first is talking about how to find the asymptotes. Alright, let's begin by talking about how to find the vertical asymptotes. And I'm going to begin by using the simplest rational function you can think of, 1 over x. And we're going to start here, and we'll get more complicated as we go along the way. By the way, your book oftentimes, instead of writing y here, they use f of x. That's okay. Either way you want to write it is fine. I'm going to use y just because it's a little less writing to do. F of x just implies that the function is an output value for this input value. All right. Now, if you recall from the previous lessons, this denominator cannot be equal to 0. Whatever is down here on the bottom cannot be 0 because an equation or a fraction is undefined if the denominator is 0. So in this particular case, the vertical asymptote happens to be what the denominator cannot be, and what the x can't be in the denominator. So in this case, the vertical asymptote is that x cannot be equal to 0. Now, as we get into more difficult functions, that means the asymptotes may not be 0, might be others. Now let's go ahead and graph this. If x cannot be 0, we're going to draw that asymptote in. Now, it's going to conflict a little bit with the y-axis, so just so that I can see it, I'm going to put it right next to the y-axis as a dotted line. Okay, put it right here. Okay, it's there. It's right on top of the y-axis, and we're going to go ahead and graph it. Now we're going to need to make a table, and when we do that, right in the center of your table, we're going to put that undefined value, 0, because 0 is undefined in this particular function, and that happens to be our vertical asymptote. I'm going to use the letters VA here. And we're going to pick values kind of on both sides of that line. Let's go -1, -2, -1, -2, and -3, and then down here 1, 2, and 3. Let's put some numbers in here. All right, let's go down here. If x is 1, 1 over 1 is 1. If x is 2, 1 over 2 is a half. If x is 3, 1 over 3 is a third. Okay, let's put -1 in there. 1 over a -1 is a -1. 1 over a -2 is a -1/2. And 1 over a -3 is a -1/3. Let's plot these and see what it looks like. Start here. 1 goes to 1. 2 goes to a half. and 3 goes to a third. As you can see, it seems to be approaching that horizontal asymptote. Okay? -1 goes to -1 here. -2 goes to a -1/2. And -3 goes to a -1/3. And again, this branch of the graph is approaching that horizontal asymptote. It appears to be. We'll talk about how to find that horizontal asymptote in a minute. But the graph looks like it's approaching the vertical asymptote down here, and looks like it's approaching the vertical asymptote up the top. And it tends to look like it's approaching this x-axis as well. Now, many of our graphs look like this, and in order to figure out exactly what they're going to, where they're going to head off into infinity, because that's what's happening, they're going off to infinity here, we need to know where these asymptotes are. So let's try another one, and then we'll practice taking a look at horizontal asymptotes as well. All right, let's take a look at this one. And you notice I've complicated things a little bit by not only putting a number on the bottom, but I've also added an x on the top. Let's start the same way we did before. We're going to find that vertical asymptote by setting this thing in the denominator equal to 0 and solving it. X has got to be 3. That tells us that x cannot be 3, and it has to be a vertical asymptote. So let's go ahead and graph that vertical asymptote at x equals 3. 1, 2, 3. There's a vertical asymptote right at x equals 3. And I'm going to create a dotted line there. Make sure you show these in here. Now, there also possibly is a horizontal asymptote. In the last problem, it happened to be the x-axis. But the horizontal asymptotes are not discussed in your book, but I'm going to show you how to do it anyway, because it's really necessary to kind of see where the graph is going to approach horizontally. And this topic has to do with something we call limits. And limits is a way of discussing, you're going to do this in pre-calculus and also a lot in calculus. Limits is a way of discussing what happens as a number gets very, very big, as it approaches infinity. In other words, as x approaches infinity, and that's the symbolism that you see oftentimes, as x gets very big or very small negatively, what's going to happen to the y part of the equation? Well, let's take a look at this. For the moment, let's just pretend that x is approaching 1,000,000. I mean, we could use 1,000,000, we could use 1,000,000,000. They get bigger and bigger, but let's pretend that x approaches 1,000,000. What would this fraction look like? Well, it'd be 1,000,000 over 1,000,000 minus 3, or 999,997. Now, the 3 became pretty insignificant here because this is basically 1,000,000 over 1,000,000. In fact, if I let x approach 1,000,000,000, that 3 becomes even less important, right? Put another 0 on there, right? That 3 becomes even less important. In other words, that number 3 is an insignificant number in this problem. You're going to have to get used to the idea that some numbers in the problem have little meaning when x gets extremely big. Well, what is this fraction? Well, basically, as this thing gets bigger, billion, trillion, quadrillion, you're basically approaching 1. Isn't this basically 1? The y value is equal to 1. As x gets very big, 3 is insignificant, and I've got 1,000,000,000 over 1,000,000,000 or 1. So that tells me that my horizontal asymptote is at this line, y equals 1. So I'm going to draw it in there. And that means that our graph is going to approach that line as well. Now, we don't need a lot of points because we know that these lines are going to kind of indicate where the graphing is going to go. But let's make a little table here just to kind of get ourselves going here. We know that 3 is a spot where it can't be, x value can't be 3. but let's pick a value or two on both sides of it. If x is 4, this is the vertical asymptote here. If x is 4, 4 over 4 minus 3. 4 over 4 minus 3, or 4 over 1, is 4. If x is 5, 5 over 5 minus 3. 5 over 2 is 5 halves, or 2 1/2. If x is 2, 2 over 2 minus 3. Well, 2 minus 3 is a negative 1. 2 over a negative 1 is a negative 2. And if x is 1, 1 over 1 minus 3. Well, 1 minus 3 is a negative 2. 1 over a negative 2 is a negative 1/2. Let's plot these points and see kind of where they're at, and that'll tell us maybe where our graphs are going to be. 1 goes to a negative 1/2. It'll be right here. 2 goes to negative 2. 3 is a vertical asymptote. 4 goes to 4. 2, 3, 4. And 5 goes to 2 1/2. Right here. Now you can see as you look at these, just these couple of dots, you can kind of see an idea where these graphs are going to approach. And I can see that this is going to actually approach those lines, go through my 2 points and head off to infinity south and infinity west. And then this one over here, this branch is coming from infinity north and headed toward infinity east. Okay? Positive x value gets bigger and bigger. It approaches that 1 that we said it was going to be. Now, there's our graph. And basically, this is the idea, is that you're going to need to find the vertical asymptote by figuring out what the denominator can't be, and figure out the horizontal asymptote by using this idea of what happens as x gets extremely big. And you'll be able to calculate those two asymptotes. Maybe sometimes there's more than 2, and make a table to kind of get a picture of where that graph is going to be. We don't need a lot of points to get that picture here, but it helps to know both asymptotes. Let's try another one. All right, this is a problem from your homework. It's number 17, and they're not actually asking you to graph it here. They're just asking you to find out where the asymptotes are. And I want to ask you to find not only the vertical asymptote, I'd like you to find the horizontal asymptote as well. So let's start that process, okay? I want to find out what would make this denominator 0. Well, because this is x squared here, there may be more than one thing that makes this denominator 0. In fact, if I factor this denominator, and I think I can, into 2 factors, then each of these factors on the bottom can't be 0. Well, if I recall, this has got to be x plus 4 and x minus 2. If I'm going to factor this, I'm just factoring the denominator here. 4x and a negative 2x gives me 2x, and there you go. So now each of these factors in the denominator cannot be 0. So I would set each one of them equal to 0 and solve it. This is x is equal to a negative 4 and x is equal to 2. Now you may not have to do that step just because you can see that x can't be a negative 4 here and x can't be 2. That means we're going to actually have 2 vertical asymptotes in this problem. Our vertical asymptote is going to be at x equals a negative 4 and at x equals 2. So that would look like x is at a negative 4. It'd be a vertical asymptote right at negative 4 and a vertical asymptote at 2. Now notice that there's going to be 3 different branches here. Branch on the left, one in the middle, and one on the right. We're not going to take the time to graph that. That's a sizable undertaking because of all of this arithmetic that you'd have to do. But there's going to be 3 asymptotes here, and if next time I see you, we're going to talk about how to do this with the calculator. But you need to be able to tell where the asymptotes are, whether you're using a calculator or doing this manually. So there are my vertical asymptotes. Now, there's one more thing to consider, and that is, where are the horizontal asymptotes? Or maybe there's only one. Let's find out. Well, what happens to this function? What happens to y as x gets very big? Well, let's think about that. Let's say 1,000,000. 1,000,000 squared. Well, 1,000,000 squared is a huge number. I don't know, quadrillion or quintillion or whatever. That's a very big number. The 8 means absolutely nothing when you're talking about a number that huge. And even 2 times 1,000,000 is fairly insignificant as well. So basically, we've got 4 over a very big number. Well, 4 compared to a huge number is like nothing over a very big number. It's like 0 compared to that big number. This 4 becomes insignificant when we think about how big this number is. Let me give you an example here. Let's say you owed somebody $1 billion and you paid him $4 to pay it off. That's nothing. That's practically nothing. It means absolutely nothing to getting that bill paid off. Okay, I mean it's not nothing, but it's insignificant in terms of paying off your $1 billion debt or whatever. So this is basically 0. So the horizontal asymptote is a y equals number. See, it's y equals, it's horizontal. Y equals 0. So the horizontal asymptote has to be right here. Okay. Now we'll tell you that sometimes when you graph these, they do cross the horizontal asymptotes occasionally. Not always, but sometimes they do. So you've got to be on the lookout for that. And I will come back and do one of these again tomorrow on the next assignment. Let's take a look at another problem. All right, let's take a look at this problem. And this problem is going to cause us to take a little bit of a step back. Think about this just a little bit. I want to find out what the excluded values are in the denominator. So I'm going to say, well, if x plus 2 is equal to 0, that means that x cannot be a negative 2. That's true. You'll notice I did not say vertical asymptote here. And that's because there's another aspect of this that needs to be considered. And that is, what happens when we cancel away factors? If you look at the numerator here, this actually factors to x plus 2 and x minus 1. And if we cancel away the x plus 2's here, the graph that remains is quite simple. Let's cancel that. And what we have is y equals x minus 1. Y equals x minus 1. Well, that's just a line. Y-intercept at -1, slope of 1. There it is. It's just a line. So what happens here is that if you can cancel a factor, your graph may look different than the ones we've been looking at. Sometimes there may be a curve, maybe not, but the graph may look different. In this case, it produced a linear equation. So there is no vertical asymptote. I can't put an asymptote in here because it's not approaching anything. But what is significant is the fact that x can still not be equal to -2. It's an excluded value. It doesn't work in here. Even though we've canceled it away, it's still a part of the original problem. And being a part of that original problem, it's an excluded value. The book calls this a point of discontinuity. Point of discontinuity. Discontinuity. And that simply means that the graph is going along and it hits that spot and it's interrupted for a moment. And we have a point of discontinuity at -2. So I'm going to go down here to right here and I'm going to put a circle there. This is what we might call a hole, okay? And I'm going to use the phrase hole, it's just less to talk about, but a hole is a point of discontinuity. In other words, this is a line, yes. However, because the denominator has an excluded value, I can't consider -2 as one of my possible answers. as part of this graph. It's a point of discontinuity. So when you check these problems for asymptotes, you're going to be checking for vertical asymptotes and horizontal asymptotes, but you're also going to have to check them for holes. And how do you know if something's a hole? You know if something's a hole if it canceled away. In this case, see how it canceled away? We know that that must have been a hole right there. Anything that's not a hole and remains on the bottom would have been a vertical asymptote. So this is the idea of a point of discontinuity. Let's do another one of those. Okay? All right, let's take a look at this one. This is problem 19 from your book. And the book instructions say find any vertical asymptotes or holes, in other words, a point of discontinuity. Let's see what happens. And in order for us to figure out what the excluded values are, we've got to factor the denominator here. I need to know what those factors are going to be. And I can see that this is going to factor into x plus or minus something here. Let's see. What two numbers will give me -5 when I multiply and -4 when I add? That would be x minus 5 and x plus 1. Let's see, -5x plus 1x. There you go. Now, as I look at this, I can see there are two excluded values. And might think, oh, there's two asymptotes, two vertical asymptotes. But notice that this one is going to cancel away. And I'm left with just a 1 at the top. There are still two excluded values, but this one is the vertical asymptote because it did not cancel away, and this one was a hole because it canceled away. If they cancel away, they become holes. If they don't cancel away, they become vertical asymptotes. So let's take a look at the graph here. I'm going to have a vertical asymptote. Well, what would x have to be? Well, x cannot be a -1 here. I'm not going to bother solving it. X can't be a -1, so x is not a -1 here. And that's a vertical asymptote because it did not cancel away. But this other excluded value, I can see that x cannot be a -5. Excuse me, a +5. X cannot be a +5. If x is 5, that makes that value 0 as well. So I'm going to go over here. Let's change this. It's a little bit too big a scale there. Let's go -1. 1, 2, 3, 4, 5. I'm going to have a hole on my graph somewhere here. Well, in order for us to draw that hole in, we're going to have to graph this thing. And I'm going to do that here. I end up with a function. When I end up simplifying this, my function is y equals 1 over x plus 1. And I can graph that pretty readily. Number 19, they didn't ask you to graph it, but I'm going to do it here anyway. And we're going to make a little table just to see what's going on, okay? -1 is a vertical asymptote. Let's put out -2. 1 over -2 plus 1 is a -1. 1 over a -1 is a -1. Let's put a -3 there. -3 plus 1 is a -2. 1 over a -2 is a -1/2. And then down here, if x is 0, 1 over 1 is 1. If x is 1, 1 over 2 is 1/2. Let's see what this looks like. -3 goes to -1/2. It's right here. -2 goes to -1. -1 is my vertical asymptote. 0 goes to 1. And 1 goes to 1/2. So I can kind of see here that the graph is going to approach. Well, we never did figure out the horizontal asymptote. Let's do that real quick here before we try to graph this. What happens, look at my function here, what happens as x gets very big? Well, as x gets very big, I've got 1 over a trillion. This 1 doesn't mean anything. A trillion 1 doesn't mean anything. And 1 over a trillion, if I paid back $1 out of a $1 trillion debt, that's basically nothing. So once again, this is the horizontal asymptote is 0. This is basically 0 over a trillion. So the horizontal asymptote is at y equals 0. So that's right here. And it kind of looks like that when I see where the points are being plotted. So I'm going to have a graph here that looks like this. Okay. and here as well. Okay. Now, there's your graph. We've graphed it. We have an asymptote. You got to declare the asymptote. But there's one thing we didn't do, and that is there is a hole at x equals 5. X cannot be 5. So 1, 2, 3, 4, 5. Right here, a little bit small my picture is, right here, there's a hole right there. And you're going to plot that point of discontinuity. So the vertical asymptote is found by finding the thing that did not cancel away on the bottom, and holes are found by anything that did cancel away. Make sure when you graph these, you put a hole on the graph where it does not, it's not considered a value, a usable value. Okay, let's try something else. All right, let's take a look at this one. This is a problem from your homework for tonight. It's number 10. You might want to do it along with me here. We're going to check for vertical asymptotes, any holes, and we're going to check for the horizontal asymptote as well. We're going to do this at the beginning. It gives us a lot of clues on how our graph is supposed to look, even though we don't need to plot a lot of points then. All right, I can see on the bottom that what I've got is actually a double factor down there. I'm going to write it out this way. And I can see that 1 cannot be x. In fact, it can't be x twice here. And that makes it a little bit, it shows us a little something here. But x is equal to 1 would be a vertical asymptote. Are there any holes here? No, there's no holes because nothing canceled away. So I'm going to write none. Nothing canceled away, so there's no holes. And there's actually a double vertical asymptote. We'll talk about what that kind of means here in a second. Okay. Now, what about horizontal asymptote? Well, as this number in the bottom gets big, the ones don't mean much. So 1 billion times 1 billion is an enormous number, and 4 over 1 billion is basically nothing. So the horizontal asymptote, 0, paying somebody $4 out of billions and billions you owe them, is basically nothing. So this is y has to be 0. So now as we graph this, we've got a vertical asymptote at 1. We've got a horizontal asymptote at y equals 0. I'm going to put it right next to my x-axis there. And let's plot some points. What's going to be significant about this problem, and the reason I picked it, is because of this squaring here, to see what's going to happen here. So we know that 1 is going to be undefined, and it's a vertical asymptote. So let's pick some values on either side of it. How about 0 and -1? How about 2 and 3? Let's put some numbers in here. I'm going to use this one here. It's probably a little easier to work with. Let's put 2 in there. 2 minus 1 is 1. 2 minus 1 is 1. 1 times 1 is 1. 4 over 1 is 4. Let's put 3 in there. 3 minus 1 is 2. 3 minus 1 is another 2. 2 times 2 is 4. 4 over 4 is 1. Let's go up here to put 0 in there. 0 minus 1 is a -1. 0 minus 1 is another -1. -1 times -1 is a +1. 4 over +1 is 4. Put a -1 in here. -1 minus 1 is a -2. -1 minus 1 is another -2. -2 times -2 is a +4. 4 over 4 is 1. Now you'll notice that our output values did not have any negatives, and that was because we ended up, if we had a negative on the bottom in one of these factors, it ended up being multiplied times another negative and became positive. So let's see what this graph would look like. 0 goes to 4. -1 goes to 1. 2 goes to 4. And 3 goes to 1. Right there. Now this is a little unusual that we haven't seen this before, But if it's going to approach this horizontal asymptote, it looks like what we've got here is a curve here and a curve here. Now, this is different than the one we had in the past, and as I mentioned before, these rational functions, the graphs all vary quite a bit. Why do you suppose this one is symmetrical? Well, it is symmetrical because on the denominator here we had an x squared. And when that happens like this, where a particular binomial is squared, we will get a symmetrical graph. Usually what ends up happening when we graph rational functions is they head off to infinity, and then the other graph comes in from the other hemisphere. It comes in from the bottom. But because of this is kind of a double asymptote here, it came in from the same place it left. This whole idea that these approach asymptotes and then they come in from the other direction was kind of upset by this particular problem. All right, let's do one more just to kind of underscore this here. We're going to start by looking at vertical asymptotes, any holes that appear, and then the horizontal asymptote. All right, vertical asymptote. Well, if I can simplify this thing, maybe there isn't one. Let's find out. If I factor the top, which is the difference of squares, I got x plus 1 over x minus 1. So the first thing you're going to want to try to do is factor these to see if they factor. And in the book here, that most of them, they do factors for you. So now, as I factor the top and I have a bottom here, I can see that these two are going to cancel. But there's an excluded value at 1. X cannot be 1 right here. But it isn't a vertical asymptote because it canceled away. This has to be a hole. X cannot be 1. So there are no vertical asymptotes in this problem. Let's check for horizontal asymptote. Now I could check it at the top here, or I could check it here and see what happens here, but what I end up with after I've canceled is this. Well, what is that? Well, that's a line. Y equals mx plus b. And if I graph this, y-intercept is at 1, slope is 1, rise of 1, run of 1. I have a line, I have a line right here. So it's a line, and so it doesn't have a vertical asymptote, and it doesn't have a horizontal one either. None. There's no horizontal asymptote that the line's approaching. So sometimes, again, when you cancel things away, you create shapes that, don't look curved. They're not necessarily curves. But I have an excluded value where x cannot be equal to 1. So I'm going to go over here where x is 1, which would be right here, and I'm going to draw a hole in there because it's an excluded value. So there's your graph. Now tonight you're going to be graphing these manually. I'm going to show you how to use the calculator tomorrow to check your work. Some of you may try to figure it out on your own. That's okay. If you do try to figure it out on your own, just make sure you're using lots of parentheses, because it's real easy to end up dividing incorrectly with your calculator. Let's take a look at your homework for tonight, and I'll come back with some more work tomorrow. All right. Right now this might look a little confusing to you to do this, but you'll get it. Understanding how to come up with the vertical asymptotes is fairly simple, and you'll get used to the idea of coming up with those horizontal asymptotes. And then holes, of course, are anything that's canceled away. Once you have that, you make a little table, try to plot some points. Be careful with your arithmetic. So here's your homework for tonight. For a while, we're going to continue to call these assignments by alphabet letters, but at the end of this chapter, we're going to convert over to assignment numbers with regular integers instead of these alphabet letters. Please practice all the problems. I'm giving you lots of odd ones here for you to check in the back of the book. You've got some even ones as well here. Do the best on this that you can, and I will go ahead and show you how to use the calculator tomorrow to check your work. And sometimes the calculator is real helpful in coming up with a table, so you don't have to make your table all by yourself. So, all right. See you later.